Thank you. All right, then let's get started. Thank you, everyone, for joining me. As Natasha said, my name is Muir Manders. I work at Retail Next, which, for the curious, does analytics for brick-and-mortar retail stores. We're headquartered in San Jose, in California, but we have offices here in Nizhny Novgorod and in South Africa. All right, so today I'm going to be talking about static analysis in Go. So first, a quick overview. I want to emphasize that the point of my talk today is to encourage other developers to look at static analysis tools and even think about writing your own custom static analysis checks for your code base. There's a lot of existing tools out there, but often your team and your code base can benefit from having your own specialized checks, and we'll see examples of that later. So today I'm going to talk about, first, I'm going to define what static analysis is and why it's useful. We're going to look at how to invoke the Go static analysis tools, and then we'll look at some examples of writing Go static analysis tests. And today, of course, I'm showcasing Go, but I encourage everyone to look at what languages and tools, what tools are available for the languages that you use. Okay, first, what is static code analysis? So simply, it's analyzing code without running it. And linters are a common example of programs that perform static analysis. I assume most people are familiar and probably use linters. So our team uses static analysis for mainly two purposes. The first is to check for certain kinds of programming errors. So here I've got a snippet of JavaScript code where anyone who's programmed in JavaScript probably is familiar with this bug, where if you declare a variable in your loop, it's actually scoped for your function, not for your block. So this user object, if you use it in some sort of asynchronous call, you're going to have a bug here where it's going to be the wrong user. So this is a classic JavaScript blunder, and this is a good example of the kind of problem that you can detect with static analysis. And the other main reason we use static analysis is to check for adherence to code style guidelines. So we like all of our code to be styled the same, formatting and white space and all that stuff. So we use static analysis to make sure that everything remains easily readable. So here's an example of, Johnny Hot Coder joins your team, and he's got his own weird style to write stuff, and you want to kind of just make sure everyone writes the same looking code, so you can use static analysis tests to ensure that. Okay, so now let's talk a little bit about Go. If you don't know, Go is a programming language created at Google, and I think it's particularly well suited for static code analysis. So first, of course, it's statically typed, which means you can know the types of all your objects just by looking at the code, which makes it easy to write really powerful static checks. The second, the compiler toolchain, specifically the parser and the type checker, they're written in Go themselves, and you have access to them in the standard library, so you can write your own tools that kind of leverage the same things the compiler uses to do sophisticated checks. And finally, it has a relatively simple syntax and a relatively small set of language features, which just makes it easier to perform the analysis because you don't have to think about as much stuff in your head. You don't have to remember, how many interesting, complicated features there are in the language. It's kind of simple to reason about. Okay, so for static analysis, normally the first step is to parse your code into an abstract syntax tree. It's just easier to work with a tree data structure than it is to work with the text directly. So for a quick review of what an abstract syntax tree looks like, we have a little snippet of code here, and then this is what the abstract syntax tree might look like for this code. You have a root node that represents your if statement. You have one child, which is the condition of the if statement, and this is a binary statement, so we're looking at this right here. And then it has children representing the a equals 0. The if statement has another child, which is the block of code to run if the condition is true. And it has a single child, which is the return statement, and that has a single child, which is the true argument. So this just kind of gives you a refresher on what an abstract syntax tree looks like. So let's look at how you actually generate the abstract syntax tree in Go. And before I go into this example, I want to point out that all these packages that I'm using, these are all in the standard library in Go, so there's no extra stuff you have to download. This is all kind of built in and ready to go. So we've got this sample function up here that returns the square of a number, and we're going to parse this snippet into the abstract syntax tree. So first we create this file set object, which just tracks what files you've looked at and the positions of all the lines in the files. And then we call parser parse file, and we pass it the name of our file, which is square.go. And that's it. This returns the parsed abstract syntax tree object for the file. And you'll notice here that I'm ignoring the error return code. Obviously, if you do this for real, you should check your errors, but for brevity, I'm ignoring errors. So now that we've parsed our tree, I have some more code here to actually look at it. So this inspect function is just something that lets you walk the tree, walk all the nodes, so you can, when you're looking for something in particular. And in this case, I'm just going to print out the type of each node so we can see what's actually in the tree in this case. So if we run our example, we can look at what's in our tree. And real quickly, our root node is our file node representing the entire file. And then there's an identifier, which in this case is the name of our package, square. And then we have a function declaration, which is obviously our function declaration. We have an identifier, which is the name of the function, function type, which has more information about our function. And then there's a field list, which is the list of arguments. And then you have another field list, which is the list of return values. And then you have a block statement, which represents the body of the function. And that contains a return statement and a binary expression, which is our multiplication. So, it makes sense to me. I hope it makes sense to everyone else. And one thing I wanted to point out, my last example, I'm just showing you the types in the tree, but there's actually a lot more information. It has all the details about your code is in the tree. So in this example, I'm going to just print out the entire tree so you can see. And we're looking at a simpler snippet right here. So similarly, you can see the root is a file node, and you have a identifier, which is the string variable, which is the name of our package. And our package, details aren't that important. I just want you to see that it has all the information contained in the tree. We've got our declarations, and we have a value spec, which corresponds to our variable declaration here. And you can see the left of it, we have a myvar identifier. And on the right side, we've got a literal integer value 1, 2, 3. So everything checks out. So let's go into some examples of how to actually use the abstract syntax tree to do some extra checks on our code. So this is a contrived example. I've just made it up. It's not very interesting. But pretend you're reading through some code, and you come across this function right here. And it's important you understand it, but you see it's calling these functions that have one-letter names. You don't really know what they're doing. You look at the functions, and they're not very easy to understand. So you're kind of frustrated that the author didn't make it easy for you to understand. And ignoring the fact that there's no documentation, you realize it would at least be helpful if the functions had better names. If they had descriptive names about what they did, then you could probably just understand it without worrying about the details. So you decide you want to write a test that enforces all functions have at least 3 letters in the name to try to prevent this problem in the future. So let's look at what that test would actually look like. So as before, we parse our file into the abstract syntax tree, and then we walk the nodes in the tree. And in this case, we're looking for a function declaration node, which is, of course, going to correspond to these function declarations. And then we simply say, if the name of the function is less than 3, then we're going to print out a warning message saying your name is too short. So we can run this and try it out. And sure enough, it says P is too short, Q is too short, and it didn't give an error about important code because that name is long enough. Okay, so let's move on to a more interesting example. So if anyone has used Go, you probably have used the standard library time package for dealing with time. So there's one kind of gotcha that you learn about when dealing with time objects, which is if you compare two time objects using equals equals, it probably doesn't do what you want. You're supposed to use the dot equal function, which just compares that the two epoch times are the same, whereas the equals equals function compares all the inner attributes of your time object, including the time zone and the monotonic clock value, other stuff you just don't want to compare. So in this example, we're getting a single time object, and I'm putting it in two different time zones, and then we're going to look at if they compare equals equals and if they compare dot equal. So let's run it. Of course, equals equals returns false because they're in different time zones, and the equal method returns true. So it's almost always a potential bug if you use this equals equals operator. So we're going to try to write a check that catches any places where we do that. So let's start like we did before. We've parsed our file into the abstract syntax tree, and then we start walking across the nodes looking for, in this case, we're looking for a binary expression, because that's what this is. It's a binary expression with something on both sides of the equal sign. So we found our binary expression here, and this is what it actually looks like, our little object here. We can see we've got an expression for the left side, we've got an expression for the right side, but we don't really have a way of knowing if the left and right side are time objects or not. They could be integers, they could be strings, they could be function calls. So we need a way to know the types of the nodes we're looking at. So fortunately, Go makes the type checker available in the standard library. So the type checker works by you give it the parsed abstract syntax tree, and it calculates a lot of useful information about the types of all your objects. So it calculates the type of every expression, which is something we'll use for this example. It calculates the definition and use of every object, which I'll get to later what exactly I mean by object. And it creates mappings to go from your abstract syntax tree into the kind of typed objects that those nodes represent. And it also gives you information about the scopes of your code, all of the variables declared in the scopes, the child scopes and the parent scopes. The scopes are useful for certain types of static analysis. So I want to point out here that knowing the type information is very useful. At this point, you're essentially as powerful as the compiler, so you can do lots of cool checks. You can make them as complicated as you want, but often you can get a lot of value out of a very simple check. And I think many other languages make the abstract syntax tree available, but I don't think there's many languages that make it easy to get the type information. I could be wrong. Hopefully I'm wrong, because it's very useful, but it's very easy to do in Go. Okay, so back to our example for the time equals equals check. As before, we start by parsing the file into its abstract syntax tree, and then we've got some more code here to actually invoke the type checker. So we start with a config object, which can control some of the features of the type checker, and the only required argument is the importer object, which controls how the type checker goes to load other packages that your code references, and in this case, we can just use the default importer. And then another input to the type checker is this info object, and this is just where the type checker stores some of the stuff that it calculates for you. And in this case, we want it to give us the mapping of expression nodes to the type and value of that expression. And this is type and value because if it's a constant expression using just constant values, then you can know the value of that expression at compile time. So sometimes you can even know the value, but we only care about the type in this example. So moving on, back to our check here. So we've got some more kind of stuff we can get ready before we walk the tree. Now, since we've got the type information, we can import the time package. So now we have an object that kind of represents this other package. And then inside of that package's scope, we can go look up the time type itself and get its type. So now we have an object that kind of represents the type of our time objects. So this is what we're going to be looking for when we walk the tree. So we walk the tree, we look for our binary expressions, and now we look at the thing that's on the left. X was the thing on the left of our binary expression, and we simply say, is its type time.time? So does it correspond to a time object? And if it does, we say, you should use equal to compare your times and not try to compare them directly. So let's run this example. And as expected, it says you should use equal to compare the times at line 17. And you'll have to take my word for it that this is line 17. So it's saying, don't use equals equals here. You should use dot equal. So this is a potentially useful check that anyone might actually find value in their code base. Let's look at one final example that I think is probably the most advanced and most interesting example. So this comes from our code base. We have an object we used for iterating the database that looks like this. It's kind of a generic interface, and it has a next object, a next method, which will advance the iterator and return true or false. It returns false if there's nothing left to read out of the iterator. And then at the end, there's a close method you call, which will propagate errors from the database. So let's look at a quick example of how we use this object normally. So you call some function because you want to get all your users, and you pass it a pointer to a user object. And you've got your iterator object, and then you just kind of loop over it, and for each user, you print out the user's name in this case. And then when you're done, you call the close object, and you check if there's an error. You probably have to do something. Of course, that case was fine. The problem comes if you forget to call the close method. In this case, instead of printing out the name, we're building up a list of all the usernames. And oops, we forget to call close. So what can happen if you get an error halfway through, your list of usernames might be incomplete. And that can lead to potentially really bad application bug, depending on what you do with the username. So of course, it's always important to check for errors. And so we want to write a test that tries to catch uses of the iterator that don't call close. So everything's getting a little bit more complicated than before, but we start with parsing. We have our type checker configuration object. And then we put one more thing into our info object. We want it to also tell us about the mappings of identifiers in the abstract syntax tree to the typed object they represent. So this kind of allows us to go from the names of things in the abstract syntax tree to the actual type object that they represent. And we invoke the type checker. And then like before, we look up a particular type. In this case, we look up the iter type that we're concerned with in this example. And then we go one step further, and we look up the next and the close methods. So what we've done here is we actually have an object here that represents this method on this type. So if you have another method called next on something else, it'll be a different object. This is actually the next method only on this type. And then we make a map here, which we'll use shortly. So similar to before, we just want to walk our tree. And in this example, we are looking for a function call to .next or .close. So that corresponds to the call expression node type in our tree. So once we found a function call, we can kind of take that apart further into a selector expression. It's not details aren't that important, but this selector expression is something that looks like this, where it's foo.bar, and you're selecting bar on foo. So in this case, we're looking for something that looks like iter.next, which is going to be a function call to next. So once we found a selector, we say, is the object of the kind of right-hand side of the selector the next method, which means essentially, are you calling the next method on an iterator? And we say, if you're calling next, then we're going to look at the object of the left side of the selector. So we're essentially going to get the object representing the iterator and store it in our map. So we're going to see this code here. We're going to say, oh, you're calling next. We're going to take iter, and we're going to store it in our hash map to remember it. And here it's important to understand that when we get the object of our iterator, at this point, the type system knows that this iter, and this iter, they're all the same object. In the syntax tree, they're kind of separate nodes that happen to have the same name, but the type checker knows that they're the same object. So it allows you to do cool checks like this. And then same thing, we look for calls to the close method, and whenever we find close, we delete the iterator object from our map. So we're essentially tracking places where we've called next, but we don't call close. If all the objects call close, our map is going to be empty because they've been deleted. So at the bottom, we just say, okay, anything left in your next calls is a place you've called next but haven't called close. So we print out a warning. So if we run this example, oops, it says, yeah, your iter is missing a call to close at line 53. Go back to our example here. Line 53 is actually going to be this line where it's defined. It's saying the iterator object that's defined here, you forgot to call close. So this is a useful check. I mean, there's something to be said about maybe the interface itself could be changed to help avoid this, but we feel that this iterator interface is kind of the simplest and most flexible. So we get a lot of value out of this check to make sure that everyone closes their iterators. Right, so this test is not perfect. You get a case like this where obviously close is never actually going to be called here. So this will trick our test, but in general it's better to assume that your coworkers are not adversarial and they're actually trying to write correct code, so you can kind of ignore weird stuff like this. And another thing to point out that maybe you noticed, we're checking that it's calling close, but we're not checking that the code is actually looking at the error and propagating it. So that's another improvement you can make to the test, is to make sure that the code actually does something with the error. All right, so that's our last example. So let's talk a little bit about challenges in Go for static analysis, because it's not perfect. There's some cases where it doesn't really work. And in particular, so Go has the empty interface reflection combination, which is often used for kind of type unsafe generic programming. We have the unsafe package, which allows you to do arbitrary pointer casts in memory, anything you want basically. And we've got CGO, which lets you call C code directly. So these three things have one thing in common, which is they kind of operate outside the type system. So if you're doing anything that is outside the type system, it can break the rules, and it's going to be really hard to analyze that statically because, I mean, a lot of stuff happens at runtime for these things. So in these cases, you're kind of on your own, and you just have to do your best to not screw it up. But it's a minority of code, so most of the time you can get a big benefit from static analysis. So now I've got a few tips for writing successful static analysis tests. Probably the most important one is you want no false positives, which means you don't want tests to say there's an error when there's not actually an error, because that just pisses people off. You write some cool code, and some test is like, oh no, you've got an error here, and that and then you just hate the test and you want to delete it. So it's important that the test doesn't have any false positives, and in general, it's better to give up a little test coverage if it means you can eliminate the false positives of your check. And then second, it's important to have clear errors. The test has to say exactly what the problem is, where the problem is, and it has to be clear what the fix is. Otherwise, people are confused and don't like it. And then a third tip is you want to avoid having exceptions in your tests. So it's better to have your check apply to all your code. And if you have an exception list, don't check these files or don't check this directory, people will be tempted to just add their new files to that exception list. So it's better just to have no exception list if it's possible. All right, so wrapping up, if you're interested in writing your own static checks in Go, I recommend you read this link here, which has lots of great information about abstract syntax tree and the type system and how they kind of relate to each other. And of course, my examples look simple, but there's a learning curve if you actually want to write stuff like this. But it's not that hard once you get used to kind of walking the tree, and then you have to go between the two worlds of your syntax world and your type world. Once you kind of get used to that, you can write sophisticated checks pretty easily. And there's a few packages I wanted to recommend. We have our own package that we use to kind of reduce the boilerplate. All my examples use just the standard library, but you can kind of, make it a little easier to write by using a helper package. And of course, there's a lot of existing static analysis checks and that perform kind of generic checks that are helpful for everyone. And these are if you want to write your own checks, it's good to start by looking at other checks just to kind of see how they work and what you can do. But of course, if you want specific checks, like our last example, the iterator example, we're not going to find a publicly available static check for that because it's specific to our code. So that's something you need to write yourself. And then finally, I want to mention one more thing. If you're interested in this and you want to look at something even cooler, there's some packages in the Go tools repo that will generate the static single assignment representation of your code. And then there's some other packages to do some analysis on that. And basically, that's a special form of code that compilers often use. And if you put the code in that form, it makes it easier to do certain kinds of advanced analysis. So that's kind of an even more advanced topic. I'm certainly not an expert in that, but I'm definitely going to look into it myself. So if you're interested, I recommend it as well. All right, that's the end. Thank you.
So thank you very much for your amazing talk, Muir. And our questions are coming.
All right, in no particular order, is it possible to use custom visitors with your library or iterate or modify ASTs? Yes. So first, in all my examples, that was just the standard library, so it's not stuff written by us. And that inspect method I was using, that's just a kind of convenience function that implements a very simple visitor, but there's an interface to implement your own visitor. And to modify the AST, there's nothing stopping you from modifying it as you walk it, but it's not going to do anything useful. There's a separate package in the tools repo, so not in the standard library, that is made for modifying the AST. That's used by like GoFumt, which is a tool that kind of automatically changes your source code. It makes the white spacing consistent and does some other stuff, and that uses that package to kind of rewrite the syntax tree to tweak stuff. So that's definitely something you can do. What kind of errors seem to be undetectable with static analysis? Undetectable. Errors seem to be undetectable. So, anything that happens at runtime, like if you get weird data in or something unexpected and it causes something to happen like that, that's not going to be detectable very easily. And like I mentioned, if you're using any of reflection or the empty interface, things that don't respect the type system, that code is going to be, you can have, if you have errors in there, you're not going to be able to detect it with static analysis. And anything that's really complicated, I mean, my examples were kind of simple, but if you, sometimes you want to check something and then you realize it's actually very complicated to figure out, you know, what things could be assigned to this variable, and then this variable gets passed to this function. And some things that just end up being too complicated to check with the static test, and you just have to give up. So it's kind of, I think there's a lot of things that can be checked, but there's also a lot of things that can't be checked. Is there any best practices on where to execute static analysis on every file change, on every file save, or somewhere else? Or it depends on the size of the code base? That's a good question. So we run our static tests as just part of our integration test suite. So every push, every branch, we run all the tests, and it'll tell you if you've added new code that fails the test. It would be cool to have it also integrated. You know, whenever you save the file, I can just say, oh, you've done this. We haven't done that, but it's certainly possible. There's kind of standard Go tools that, like I mentioned, GoFumped will kind of format your code automatically, and there's also another one that automatically does your import statements. So you could just add on to that stuff and do your own whatever analysis you want and have it print out errors. So that's definitely something you could do, but it's not something we've done. Next question. Which tool is used to create this presentation? It looks gorgeous. Thank you. This tool, it's a tool called Present. It's used by people doing Go presentations mainly. It was written by Rob Pike, who's one of the creators of the Go language. And it's just, I don't think anyone knows about it except the Go community. And yeah, it only supports Go for like the code snippets and running the code. But yeah, if you ever do Go presentation, it's very convenient. And the slides are available online, and you can view them. If you go to the GitHub repo that have my slides, I have a link where you can actually play the slideshow online. Hello, Muir. Question: which codes issues are hardly covered by static analysis? Which languages do you know? Right, so I mentioned before the ones that are hard to cover by static analysis, so I think I'll skip to the, which languages do I know? Is that computer languages or spoken languages? I'm not sure. For computer languages, Go is my main one, but I've done Ruby and Node.js and C and Java and other stuff, but mainly Go these days. And for spoken languages, I've studied Japanese and Chinese as my main ones, so hope I covered it. Is there an IDE for Go where we can implement custom static analysis rules to be highlighted while typing? Absolutely. I recommend Emacs, where you can just implement whatever you want. So I know VS Code and Sublime, all those ones, they have Go packages which do the, highlight stuff based on the already available public tools. I don't use those editors, so I don't know if you can integrate custom tools. I mean, I assume you can. The modules are all just written in whatever language the IDE uses. So I would say yes, but I've never done it. I haven't seen it done. And for Emacs, of course you can. It's easy. Okay, some more questions. Do you have a library of common errors? Is it available for public use? So I have some, I've lost my thing, but my slides had a link to some existing static analysis tools that have like a laundry list of a lot of common errors, and those are kind of, those are ones that can work for everyone, any code that has this error is going to have a problem. So those ones I recommend you look at and use because they've already been written. So there are a lot of existing ones. But my talk was more about how to write custom ones, for your own use cases that no one else is going to write because they don't have your particular problem. But yeah, there are a lot of existing ones that you should definitely check out. You don't have to write every single one. All the ones you can think of for generic problems probably already exist out there. Is it possible to embed the analysis into the IDE? That's right. Similar question to before, and I would assume yes. I don't think the existing Go packages for the IDEs do this out of the box, but I assume you could if you wanted to, and in Emacs, of course, you could. Does the DB interface check you showed some covers next called after close? All right, so this is asking what happens if the call to close actually appears before the call to next, which can happen, you make a helper function or something at the top that calls close, and then you have your next calls down here. So the way, as written up there, it would not work in that case because it assumes it's going to see in order of, lexical order, it's going to assume it sees next before it sees close. But if it's the other way around, it's going to give you a false positive. So you'd have to make the check a little bit more sophisticated if you wanted to catch that error. What is the tool which you use to make a presentation? I already talked about that. Examples of bad rules, those that lead to worse code. Let's see here. Sometimes I'm tempted. Often the motivation to add new checks comes when I'm doing code reviews, and I do a lot of code reviews, and I find myself leaving similar comments. Oh, you should do this, and so I'm like, oh, maybe I can make that into a static test that kind of just gets checked automatically. And occasionally there's kind of stylistic things that is my style, but is not I don't think it's like the team style. And sometimes I'll want to make a check to enforce my style, and I have to stop myself from doing that because that would just create more problems. Because so it's important to separate, your opinions from what's actually the team consensus, and so you can definitely lead to problems if you make your checks too opinionated. Could I write a plugin for the parser? For example, I want to implement something like Java annotation systems and check it before I run my code generate. Yes. So Go already has a system for special comments that do stuff, and it's used for various things. You can have files ignored from the build system based on, operating system and things like that. There's this Go generate thing, which is like a kind of a step that can run before your build to do code generation. So there's already precedent for having special comments that do special things. And you could definitely, the comments are in the abstract syntax tree, so you could write a tool that looks for comments and does whatever you want, changes the code or, so you can definitely do that. All right, perfect timing. Done with questions.
Thank you very much. Thank you very much, and we have to choose 3.
Okay, I choose 3.
Spinning questions.
Let's see here. It's tough to choose. Tough to choose.
Randomly.
Okay, I'll see randomly. I don't want to pick favorites. It's hard to choose. They're all good questions. Hello, Muir. Which codes issues are hardly covered by static analysis? Which languages do you know? You're the first winner.
Please raise your hands up.
Congratulations. Okay, I'll pick one of the big ones. Could I write a plugin for parser? For example, I want to implement something like Java, blah, blah, blah.
Ooh.
And the third example, the third winner. Is there an IDE for Go where I can implement custom set analysis rules to be highlighted while typing?
Oh, wow. Congratulations, Dima.